So, as you can see in this slide, this void fraction of coke, sinter and pellets, they are a bit different, in fact about 0.51 for coke and pellet is 0.41, and the size of the burden, so coke is about 50 millimeter and the pellet is 12 millimeter. So, that is a big difference between this size of coke and pellet, almost 4 or 5 times, and that can create a problem in permeability, which we will see in the next slide. So, if you look at this, so here you are having a uniform size spherical particles, larger size. These are a smaller size and this is a mixed one. So, as you can see, when it is the mixed one, your void fraction really goes down quite low. When it is uniform, then the void fraction of the bed is quite high. This is showing the ratio of smaller to larger size. So, as you can see, when it decreases, your void fraction goes down, and that is where it creates the problem of permeability in the blast furnace, and one has to be very careful in selecting the proper size of material to put in. We will talk more about the distribution, how does it affect the permeability of the bed in the following slides. So, this figure shows about the schematic of iron ore particle, and this is the coke. As you can see from the previous even slide, that the size is almost 3 to 4 times different than the coke size. So, essentially one would expect a very high pressure drop in the smaller size particle than the larger one. So, the black one is representing more as coke and this one more as iron bearing material, sinter or pellets or even the ore, and the pressure drop in that section is almost 3 to 4 times higher than this. So, in fact, if you the void fraction, even if it decreases by 0.1, pressure drop almost by 3 times it increases. So, if you look at this table, so you can see the void fraction for coke is about 0.51 and for pellet is about 0.41. So, there itself it almost 3 times pressure drop would be there in this. Pellets, of course, they are more spherical and one would expect this sort of void fraction usually for a spherical particle, but coke and sinter, they are irregular in shape. So, void fraction more, the pressure drop is less in this coke, but here it is high. So, that can create a problem in the blast furnace. You have to put more air pumping power, and other thing is not only that, even about the reduction and the passing of the gas, utilization of the reduction power of the gas, and the heat exchange between the material and the gas. The another one is So, as the gas takes least resistance path to flow in any packed void, therefore, the preferential flow is always near the wall as the void fraction is highest over there. The amount of energy losses and the excess top gas temperature will decrease the efficiency of the process. So, mostly two types of flow are prevalent in the blast furnace, central and wall flow. So, if you look at here, if suppose this is a wall, so point of contact would the contact point here would be just like a point on the wall with the material. So, you would be having a very high porosity just near the wall. So, gas obviously will take the least resistance path. So, it would like to flow through this and bypassing all these channels, and that deteriorating the condition of the blast furnace in terms of reduction and proper utilization of the heat. So, one has to avoid this preferential flow. So, that there are ways by which it can be corrected. So, as mentioned here, by two types of flow are prevalent, central and wall, and this can be done by proper charging of the material. So, the center gas flow, coke and coarse burden material is at the center, which gives more permeability to the bed and thus low resistance to the gas flow. The shape of the cohesive zone is inverted, V type in this case. In wall flow case, the flow at the center is blocked either by softening and melting of the burden due to its poor distribution. So, central is less permeable. Gas flow preferentially towards the wall and the shape of the cohesive zone is W. So, these two types of cohesive zone are shown in this. So, you can see the inverted V type of cohesive zone, and this is a W shape cohesive zone. So, you put the more coarser material, in this case at the center. So, central gas flow is there. So, gas can easily pass through this region. However, in this case you put more coarser particle toward the periphery and less over here. So, you have a more central flow of the gases, though you have also a good flow in the center, but not as good as in this case. However, you can use the reducing power of the gases in this one better than in this. Now, so in central gas flow, heat losses to the wall are less due to the less amount of gas flow in that region. Consequence of this is the melting of the burden takes place near the tuya, and if it is not melted completely near the tuya, then it may lead to some chilling of the furnace due to the increase in direct reduction, and this may lead to poor melt quality. So, you can of course avoid this one by keeping a high amount of coke near the wall. So, if not checked properly, central flow can give high percentage of CO and hydrogen in outgoing gases at the top. Within the limit, the central flow gives good and stable operation to the process. So, essentially in this one, as I mentioned, most of the gases are going through the central region and is not reaching much toward the wall. So, wall side material is not properly reduced. So, while it is coming down, one will find that material near the wall is not properly reduced. So, and it is extended till the tuer zone. So, most of the reduction of this side will take place here, and that is more by direct reduction, which is endothermic in nature, and that will give a chilling effect to the furnace. So, temperature will drop down, and sometime even this may occur near the hearth. So, hearth chilling may occur, which is not at all desirable for chemistry of the metal and slag. So, one has to take a proper care of that one, and also the full potential of the reducing cases are not used in this. If it is quite porous, then without much reduction of the burden, they may pass, and top gases would be having a more higher potential, more CO and hydrogen. So, reduction potential which is not good. So, in one way you are wasting the reduction potential of the gases, and the temperature also would be higher in the outgoing cases, and these are the indicator to the operator whether the furnace is running in a proper way or not. So, one has to take a corrective measure for that, and one of the measure is increase the this wall flow toward this, and make a more uniform this reduction potential throughout the furnace as mentioned in the remedy. Another, in the wall flow, what happens in this case, cohesive zone is in W shape and the melting zone is above the tuer, which makes process less sensitive to operating parameter and more efficient. However, more refractory wear, it is a more refractory wear, and less reduction due to rapid cooling near the wall. So, fuel rate is high. So, in this case you will see the, because due to the cooling effect of the gases, though gases are passing through this, and due to the good velocity of the gas, wear of the refractory can occur, and because they are close to the wall, so cooling effect is also there, which is again then reducing the reduction power. So, this one also can may not utilize properly the reducing power of the gases. So, one has to take a sort of a combination in a proper way that it is reduction power of the gases is utilized properly, and not only that, the heat exchange should be proper. So, now and how do you do you can see the central flow. So, coke layer and more coke is deposited at the center. So, this is the center, this is the wall, and coke, as you have seen already, the void fraction is quite high for coke. So, the gas certainly will flow through this region in a much with less resistance. So, preferential sort of a flow, but furnace will run more smoothly here, and in this case you are not having that more coke at the center. So, gas will distribute, gas will go through this and through the wall also. So, it will have a better reduction, and gas utilization would be better in this. Now, how do you achieve this thing? We will come to that. Okay, in central or wall flow, at some places gas speed may reach the fluidization velocity. Coke fluidize easily due to low density. However, coke size is larger than other burden, which restricts its early fluidization. Local fluidization of coke has been observed in the operating blast furnace. This may lead to channeling if the fluidization reaches the lower part of the blast furnace. During charging, fine particles remains below the point of impact, while coarse particle flow downhill, and this phenomena is known as particle segregation. So, particle segregation is very important phenomena in the blast furnace charging. We will come to that, but due to this uneven flow which may occur sometimes, and some channel some preferential flow is going somewhere few other places, then you will find that local fluidization may occur. And as we saw in this figure, the minimum fluidization velocity for coke is 2.9, for pellet is 2.2, sinter is 2.5. So, there is not much difference really in this, because the coke size is quite high, almost 4 times of the pellet, and that is one of the reason. Otherwise, coke can easily fluidize if the size is like that, though the density of the coke is very less, 525 bulk density, and for the pellet is 2150. So, that is the main difference. So, we will show a bit about the charge distribution. So, as we said, this W shape of thing, cohesive zones, you get it when you have a bit coarse charging at the near the wall. So, you are trying to get the reduction this side also and at the center, and that type of charging is called the M type. So, where you are putting a bit coarser particle near the wall, and its shapes of the charging comes in this form, which is like a M type. So, you have also coarse particle here and here, and all this pattern depends upon the angle, segregation of the material, fines which are present in the material. That's why these all properties are very important during the charging and selecting the material when we send to the blast furnace charging system. Otherwise, will create quite a lot problem in the operation. And the other charging, it's we saw in the previous slides also, that is a B type charging, and where the material can slide more toward or coarser particle more toward the center, and where it gives a central flow, and this will give you the wall flow. And this figure shows that the gas velocity in the central flow would be quite high, as we explained before, due to the higher voidage and thing. So, that this is the gas velocity, and this is the mean size. So, mean size is also high, and size distribution this one. So, mean size is high, so gas velocity is high. However, in the M shape one, you can see that at the both places velocity and the distribution is reasonable. It is not at one side becoming very high like in the central flow, but in this even the wall side you are getting a good velocity of the gas. Then here is almost 0, here still you are reaching almost 0.5 meter per second. So, that will utilize the proper heat exchange and reduction potential of the gas. So, mass transfer, all these are important for the reducing purpose. So, this M type is more preferred. So, in V profile, the periphery flow is restricted and central flow is dominated. Thermal and reduction potential of the gases are not fully utilized. In M type profile, flow at the periphery is increased, there is a balanced flow both at the center and the periphery, and thus the thermal and reduction potential is best utilized. And eventually, the M profile changes to B profile after some distance from the top. But by the time it reaches to that, quite a lot thing you achieved in terms of thermal and reduction potential of the gases. Now, another important property of the raw material is about the angle of repose. So, it has been burden plays an important part in gas flow behavior, as we have seen in the previous slides. Therefore, can also be used to get the ideal gas flow. So, by proper distribution of the burden or control of it, you can get the ideal gas flow in the blast furnace, which can be best utilized in terms of heat exchange and mass transfer or reduction potential of the gas. So, one important property of the raw material is its angle of repose, which is shown below. From this figure, one can see that the pellets have lowest repose angle and therefore, have a tendency to slide towards the center of the furnace during the charging. So, as you can see, the coke has a very high angle of repose. So, angle of repose is from the vertical, you measure it from surface of the top surface of the charge with the top horizontal line. So, this angle for coke is quite high, though for pellet is much flatter. So, pellet used to become flat when you are charging, and in that way, however, the coke would be more able to that. These layer will not become that as flat as pellets. So, we will see. So, when usually when burden is charged, as you can see in this one, this is more about the pushing of the coke, but mostly you will look at the profile of this will go a bit like this, while profile of the coke would be much sharper. So, when burden is charged, pushes the coarse particle on the top layer toward the center. If the top layer is coke, then this phenomenon is called coke push, which is used deliberately for central gas flow furnace, and sometimes it is used as a corrective method for proper gas flow inside the furnace. So, as I mentioned previously, this gas flow can be controlled using your proper size burden distribution. This is one of the way. If you really want to increase central flow, you charge in such a way the other material that it pushes the coke, larger size particle cokes toward the center. So, permeability increases toward the center. So, gas flow increases in that. You can do also other way around. So, it indicates your charging mechanism is also very important, not the charging mechanism, the charging equipment should be much more flexible, by which you can control the distribution of the material wherever you want it. So, that is a very important thing, that you should have a proper equipment of the charging. This next figure showing the effect on the surface angle, the effect of gas flow on the surface angle of the material. So, as you can see that when the gas flow increases, so of course, in rho u square term, essentially your surface angle decreases for coke, sinter, pellets. So, flow of the gas also affects quite a lot about the angle of the burden material, and again can change the distribution. So, in that case, that also can change the layering angle. So, like in this case, if beta 2 is less than beta 1, the angle, then you will see the thickness of the layer has decreased then in this case, though of course, it is also at the angle of this. So, this contributes to that also, but beside that of course, the layer thickness decreases as you go down due to increase in the diameter, one thing, of the blast furnace. So, layer becomes more and more flatter than like this, what probably you are seeing it here. As you can see, they are becoming flatter as you go down. Okay, we will have one problem based on some size distribution. We are talking more about the size distribution in the material. So, and it is very difficult to have a uniform of one size. So, usually you have a distribution of the particles. In this example, some size distribution is also taken into consideration. So, in pegged example of pegged bed reactor in iron making are the blast furnace, sinter stone, sintering, and sponge iron making by gaseous reduction of iron ore pellets. So, this is one of the example that is given, that velocity of the gas through the bed is 2 meter per second at 500 degree Kelvin. The gas consists 60% nitrogen, 20% CO2, 20% CO, and gas viscosity is given. The void fraction of the bed is 0.35, and the pellets are in spherical shape, has the density of 4000 kg per meter cube, and the pellet diameter ranges between 4 and 15 millimeter with a size distribution function defined as given below. So, S is represented by this function, dP is the pellet diameter and m is a constant over here. So, one had to calculate the pressure drop per unit length of the bed along the gas flow direction and the minimum critical velocity for bed fluidization. So, I think you are already familiar with this. So, we will see how this can be solved. Now, the distribution of the particle is given and not directly the particle size or average particle size. So, we have to calculate first about the average particle size from this. So, the average particle diameter has to be calculated with the relation 6 by A, where A is the average specific surface per unit surface area per unit volume. So, 6 by B. So, A is the area and B is the volume here, and the distribution to be 1. So, if you put 1 and integrate it within this limit. So, 4 is the minimum size and 15 is the maximum size. So, solution of this gives you the value of m 0.224. So, if you put this value over here and then you can calculate the area with pi dp square dp, and if you integrate it within this limit, this is sort of this integral. So, probably you might have to recall from your undergraduate first year mathematics. Then you can solve this equation and that will give you the area of 258 millimeter square, and in the same way you can calculate the volume of the particles and 4 by 3 pi r cube sort of that volume, and if you integrate within that limit again, then so in this one you have to use table of integrals this, and you can get the volume about 456 millimeter cube. So, from this value now we can calculate the average diameter of the particle, which comes 10.6 millimeter. So, now once we got the average diameter of the particle, so this average diameter, remember it has been defined here, where A is the average specific surface area per unit volume. In that term, average diameter is defined. So, then you know from the Argon equation, pressure drop can be calculated in a packed bed. So, if you use this Argon equation, which you are already familiar with it, and void fraction is given, particle diameter just now we calculated, viscosity is given, and of course, even the velocity is given of the gas, which is 2 meter per second, and that is actually a superficial gas velocity. So, if we put all these, so all the terms are known, which gives you the pressure drop of 3452 normal per meter Newton per meter cube, and that is the pressure drop in the bed. Now, so that gives the answer of the first question, pressure drop per unit length of the bed along the gas flow direction and minimum critical velocity of the bed fluidization. So, for the fluidization, as you know, first you have to find out the Galileo number, and that we have to check. Now, it is asking about the minimum critical velocity. So, minimum critical velocity has to be related to the minimum particle size diameter. So, we have to consider 4 millimeter, that particle diameter, which is the minimum one. With respect to that, we have to calculate the minimum critical velocity, because this is the one which will fluidize first. So, if we calculate the Galileo numbers, now because gas also has this mixture, it is not the one which has 60% nitrogen, 20% CO and 20% CO2. So, CO also has the same molecular weight as nitrogen, so 28. So, with the respective percentages it can be converted, one can easily with the volume of the gas and other thing, one can get the gas density about 0.76 kg per meter cube. So, now we got rho S, rho G, rho S is given already about 4000 kg per meter cube, viscosity is also given. So, everything is known. So, if we put these values into this formula, get the Galileo number of 2.1 into 10 to the power 6, and once you put this Galileo number, again you are aware of this formula which we sort of deduced it from the first principle in the starting. So, if you put the Galileo number in this, you can get the minimum fluidization, Reynolds number at the minimum fluidization, which comes around 262, and from that you can easily calculate the minimum fluidization velocity. So, everything again is given, you got the Reynolds number. So, your minimum fluidization velocity would be 2.6 meter per second. So, the critical velocity, which means this reactors should not operate more than 2.6 meter per second velocity, and as such it is given the nominal velocity is 2. So, below fluidization velocity anyway it is operating. So, none of the particle will fluidize in that condition. Okay. So, I think you got the idea from this size distribution, how it can affect and how you can select the velocity. So, this velocity operating velocity is not related to the larger size particle, it is much related to the smaller size particle. So, you should be operating your reactor with the smaller size of particles. So, they should not get fluidized.